Hello everyone and welcome to the channel. I'm Emmanuel, I'm a Boeing 737 pilot and a member of BMDG's tech team. In today's video we'll discuss the pressurization system of the Boeing 737NG. The system is during all phases of flight controlled by the cabin pressure control system, and the system includes two identical automatic controllers available by selecting auto or alternate and a manual pilot controlled mode. Note that the auto and alternate controllers are basically cycling between each flight. So on flight 1 you will have controller A controlling the auto position and controller B controlling the alternate position. Flight number 2 it's changing, controller B will become the auto and controller A will become the alternate. And that's why it's alternating between each single flight. The manual position is always the same in that it is pilot controlled. The system uses bleed air supplied through the air conditioning system, and the actual cabin pressurization and ventilation is controlled by modulating the outflow valve and the overbought exhaust valve. Note that it's mostly the outflow valve that's controlling the system. So imagine it like this. You always have the same amount of air entering the cabin, and by controlling how much air is discharged overboard through the outflow valve, you can then control the actual cabin pressurization. The overall system works like this. When the airplane is at the maximum certified ceiling of 41,000 feet, the cabin altitude is around about 8,000 feet. We can see the cabin altitude versus flight altitude table up here below the cabin controller. And while we're talking about the layout of the panel design itself, there are two different panels available. Both, however, work the same way, so I'm not going to go into showing you the other panel on this very video. I have made a video, however, introducing the new pressurization panel that we currently see in the flight deck in here already. So, data for the system is provided by the Air Data Inertial Reference Units, the ADIRUs, by providing ambient static pressure, barometric corrected altitude, non-corrected altitude, calibrated airspeed. And the ADIRUs as well receive barometric corrections from the captain's and first officer's baro reference selectors, which is why when we're looking at the pressurization schematic up here, we actually have those in view as well. Now, the pilot is going to enter the planned cruising altitudes into the panel, and there are two different philosophies over here. Most pilots would enter the first cruising altitude that you plan to climb to, and disregard any step climbs. The reason behind that is that you would not accidentally activate the off-scheduled descent function if you don't execute the step climb that you have planned for later on. The actual flight manuals, however, ask the pilot to enter the highest expected cruise altitude, so you would enter the highest altitude, including planned step climbs, into the flight altitude as per the manuals. That, however, bears the risk that if you start descents before you have actually climb to the highest altitude, for example in case you do not get a step climb from air traffic control, then the automatic return to departure airport function is activated, descending the cabin altitude back down to the departure field elevation. So you have to make up your own minds as to what you want to do. As said, most pilots would put the first cruising altitude in, and then when you do a step climb, dial the flight out up to the next higher altitude that you're climbing to. Below that we have our landing altitude, and in there you simply insert the landing altitude of your field, and it doesn't really matter if you round it up or down. This is provided in 50-foot increments, so in the end, after landing, your outflow valve is going to open anyway, so the cabin will then pressurize to the correct outside pressure. Do note that there is one case in which the land altitude setting is ignored, and that is if you start a descent before you have reached the flight alt dialed in here, and then the cabin is actually descending back to the departure airfield pressure, And the departure airfield pressure is actually stored by storing the cabin pressure when you're on the ground on your departure airfield. Once you're in flight, when you change the flight altitude setting, that stored departure altitude is being erased from the system, so then it will always descend the cabin back to the landing altitude setting once a descent is initiated. Let's talk a little bit more about the system itself. So normal discharging of the air is controlled by the outflow valve, which is DC driven, as we can see in the schematic over here. And as I told you earlier on, the air that's leaving the cabin is primarily controlled through the outflow valve. However, just for the sake of completeness in here, a small amount of air is also exhausted through the toilet and galley vents, miscellaneous fixed vents, and by leakage of the seals. You can sometimes hear that when you are close to the main doors in flight, that you might hear a very small sound of air leaking from the doors. That is entirely normal. There are pressure relief valves installed in the airplane, 2 of them, which provide a safety pressure relief by limiting the differential pressure to a maximum of 9.1 psi. There is also a negative relief valve present, which opens when the external atmospheric pressure exceeds the cabin internal pressure. Those are the valves that we can see down here in the system schematic. To put it very, very easy, the way this works is you have a spring with a ball sealing the actual opening, and when the pressure internally becomes too big, or the pressure difference becomes too big to the outside, those balls are being pushed down, then air can flow out, and the same the other way around with the negative pressure relief valve. Now that is a very, very simplistic explanation, and I'm very sure that any engineer is actually going to kill me for it, but that is just to give you a basic idea of how you can imagine these things to work. Now, going on with the cabin pressure control system schematic over here, we can see that we have an input from the air-ground safety sensors, and that is basically to provide opening of the outflow valve to the full open position once the aircraft has landed and is taxiing in, to fully equalize the cabin pressure with the outside pressure when you are on the ground. The airplane is also equipped with an overbought exhaust valve, and on the ground or in flight with low differential pressures, the overbought exhaust valve is open, and warm air from the E&E bay is automatically discharged overboard. In flight, with higher cabin differential pressures, the overboard exhaust valve is normally closed and the exhaust air is diffused to the lining of the forward cargo compartment to provide heating of the cargo compartment, as I explained to you in the previous video on the air conditioning. Now, there is a safety function installed in the airplane for the overboard exhaust valves, which operates slightly different depending on whether you're in the 737-6 or 700s, or whether you're in the 737-8 or 900s. And in the 6 and 700, the overboard exhaust valve is driven open if either pack switch is in high and the recirculation fan is off. That allows for increased ventilation in the smoke removal configuration of the airplane. In the 8-900 it's slightly different because you have 2 recirculation fans, so the function operates the same with the exception that only the right circulation fan is being taken into account. So if the right recirculation fan is off and either pack switch is in high, the overboard exhaust valve is driven open in flight to increase the ventilation and allow for smoke to be removed easier. From here on, let's move on to the pressurization outflow schematic. So basically, as we can see in here, air is mainly coming in from the top, so from the ceiling, and is then driven through the floor down here into the cargo compartments, and from there it's flown backwards where the outflow valve is connected at the back of the airplane. So let's talk about how the auto mode operates in the 737. Basically, as I told you, in either auto or alternate modes, both modes operate to the same standard and with the same controllers, exchanging every flight. Basically what the airplane aims for is to get a constant differential pressure depending on your flight. So when we are talking about cabin altitude, mainly what we're talking about is the actual pressure inside, and it's only being calculated into an equivalent of an altitude to make it a little bit more understandable for pilots. But the overall system itself is mostly operating based on the actual pressures. So with a flight altitude selected to or below 28,000 feet, the airplane is aiming for a differential pressure of 7.45 psi. With a flight out between 28,000 and 37,000 feet, it's aiming for 7.8 psi, and above 37,000 it's aiming for 8.35 psi. The descent mode is automatically activated when the airplane descends 0.25 psi below the selected flight altitude, and then the cabin begins a proportional descent to slightly below the selected landing altitude, and that is to avoid rapid changes in altitude resulting in rapid changes in pressurization. So when you are operating the system in manual mode, then the pilot has to drive the outflow valve manually and can use the table that is provided just below the cabin pressure controller to select or to drive the outflow valve in order to provide for adequate pressurization. If you are operating the system in manual mode, be aware that a single click on the open or close button up here in the respective direction is going to result in approximately a cabin rate of climb change of around 500 feet a minute. Now, that is the same in the real aircraft, and it actually makes controlling the cabin pressure pretty hard, in terms that you have to be very sure that you are not accidentally over-controlling the altitude. So be very careful if you're operating in manual mode. So when you are talking about the pressurization system, there are basically two failures that can occur here. One is the auto-fail, and the other is off-scheduled descent. Well, let me quickly put the light test on over here so that we can see those lights in action. So we have auto-fail and off-scheduled descent. Now, let's talk about them real quick. The auto-fail light illuminates when any of the following occurs: a loss of DC power, a controller fault, an outflow valve control fault, excessive differential pressure greater than 8.75 psi, excessive rate of cabin pressure change, which is around about 2,000 feet a minute at sea level, and then high cabin pressure altitude above 15,800 feet, if the controller is not responding properly. So if the controller is responding, then the last 3 points are actually not valid. So excessive differential pressure, excessive rate of pressure change, and high cabin altitude, if the controller is responding properly and tries to correct the condition, are not going to cause the auto-fail. Otherwise, the auto-fail is actually being caused. So with the illumination of the auto-fail light, the pressure controller automatically transfers to the other controller into alternate mode. So if the auto-fail goes on, alternate is going to go on, provided the switch is in auto, and then you have to carry out the associated non-normal checklist while the system is trying to correct its problem in alternate mode, but the checklist is going to guide you further on this one. Once you move the pressurization mode selector to the alternate position, it is going to extinguish the auto-fail light. However, the alternate light is going to remain illuminated to indicate a single channel operation. Needless to say that maintenance action will be required afterwards. The other light here is the off-schedule descent, and as I briefly explained earlier on, that one is going to illuminate when the airplane starts a descent without having reached the pre-selected cruising altitude. So this is designed for the condition where you have to abort a climb and are actually returning to your departure airfield. However, it mostly happens when you have set the flight out to a higher altitude and have started the descent without having executed the step climb. Now, the off-schedule descent non-normal checklist is going to direct the pilot to select the flight out to match the current altitude, and that is basically going to solve the problem. Be aware that according to the Boeing checklist instructions, it is permissible to execute any checklist from memory, provided no hazard is created. So if you're in a descent and the off-scheduled descent light illuminates, it is permissible for you to reset the flight alt to the present altitude without having to get out the QRH and carrying out the complete checklist. And that is then going to restore normal system operation. And be aware that this capability is lost when the flight alt indicator is changed in flight. Alright, let's quickly talk about the actual cabin altitude indicator over here. So we have two needles in here, and they pose quite a threat here, because we have a big needle that's showing us the differential pressure, and we have a small needle that's showing us the actual cabin altitude. Now, when you are checking the cabin differential pressure and cabin altitudes during climb, you're looking at about 2 psi differential pressure during the after takeoff checklist, 4 psi during climb in 10,000 feet, then looking at about 7 psi when you're passing around 20,000 feet. Now, be aware of one big threat over here. During normal operation, passing 10,000 feet, the big needle is at the 4 position, and the small needle is still approximately close to the 0 position, because the cabin altitude has not significantly increased in this time. However, if you are flying unpressurized and you're passing 10,000 feet, the small needle will be around the 10 position, so quite close to the 4, while the big needle is going to indicate 0 because the inside pressure equals the outside pressure. So a reversal of those two needles, for the case that you have forgotten to set up the pressurization system correctly, is looking very similar to one another. That poses a big threat to operation in the Boeing 737NG, and this is something that pilots have to be very aware of when flying this airplane. Apart from that, one more threat that we have over here is that the needles do not have a mechanical stop at the 0 position. So if you are manually pressurizing the airplane and you pump the cabin up to a pressure higher than the sea level pressure, your needles are actually going to go below the 0 setting, which might make it look like you are actually at a very high cabin altitude. There has been a case in my airline where this happened, and basically the pilots had a pressurization problem. They executed the memory items, switched the system to manual, and closed the outflow valve completely. But then they initiated the emergency descent without checking that the system is actually reacting properly. And in this case, the system did react properly, so it was simply a failure of the cabin pressure controller. But in manual mode, the system worked properly, so an emergency descent would not have been necessary in this case. However, since in the simulator, this was later found out in the investigation, since in the simulator you always do the emergency descent, because that is just how the simulator exercises are designed, the crew actually did that on the line as well. So now, while the crew has been descending, which of course took a couple minutes to get down to 10,000 feet, the cabin has actually been pressurizing again. And it's been pressurizing so quickly that by the time they reached 10,000 feet, the cabin altitude was actually below sea level, so the needle was anywhere here in the region of 37,000 feet on the indicator, while the actual cabin altitude was anywhere like 4,000 feet below sea level, if I remember correctly. And this led the crew to believe that the cabin altitude was still at 37,000 feet, and after all this caused quite some confusion, and they ended up opening the outflow valve completely, thereby rapidly increasing the pressure from minus 4,000 feet up to 10,000 feet, causing severe health issues on the ears, because many passengers suffered injuries in their ears when this happened. So be very aware that the needles don't have a mechanical stop at 0, they are going into the negative position. However, this is the case on the real airplane, but not on the full flight simulator. So I can't tell you 100% how that's actually going to behave in the PMDG. So just be aware that this might be the case, and don't get yourself confused when you have lots of pressurization. So be very careful when you're executing the memory items, turning the selector to manual and closing the outflow valve. Be very careful there that you are actually not driving the cabin into negative cabin altitude. Eventually the negative pressure relief valve is of course going to prevent any damage to the airplane, but as in many cases, it is more likely to get damage to the passengers before you actually damage the airplane. Alright, this shall conclude our look at the cabin pressurization system. I would like to thank you very much for joining. If you enjoyed the video, I would appreciate a small donation through the Buy Me a Coffee link that you can find in the video description below. Until then, I'm looking forward to see you all again on the next one, and hope that you are enjoying your flight in the PMDG 737s.